in this video I just want to clarify a few things about the preceding videos. So the first thing I want to talk about is the difference between a total derivative, say with respect to t, and a partial derivative. And this curly d here is how people normally write a partial derivative. I just want to explain the difference between these two. And so in the last few videos, I wrote this full d here, indicating a full derivative, when what I really meant was a partial derivative. But at the time I decided to just go with it, and now I'll explain it. So say we have this function. It's a function of both position and time. We're taking the time derivative, right? So full derivative and the partial derivative. So in the last two videos, what I've meant is the partial derivative. And the partial derivative is just when we say that we're going to watch, in this case, we're going to watch t change and see how the value of this function changes. But we're going to act like x doesn't change at all. So in the example of the wave, we're just looking at one particular point on the string, and we're just looking at that x value and watching t change. So the way to evaluate this integral, or not this integral, this derivative, is to well, just take the derivative of f with respect to t, and x we're treating as if it's a constant, so it doesn't factor into the derivative in any way. But if we were taking the full derivative, if we didn't just pause time and just pick one x position and let time change, then we would have to take into account the fact that for a general function, x might depend on t. So the way to evaluate this derivative is to take the derivative of the function, just the derivative with respect to t, so the partial derivative with respect to t of f. But then also we have to add a term. We have to add a term taking into account the fact that maybe x does change with t. So this will be the derivative with respect to x. So this is how much f changes as x changes, and then we have to multiply it by how fast x changes with t. So we look at how much this changes just based on t, and then we have to think about if x changes, well, we have to say how fast does f change as x changes, and then as we're going through time, how fast does x change as t changes. And I've gone through this pretty quickly, and if you haven't seen it before, this might not make sense, but for those in the audience who have seen multivariable functions and done calculus with them, it's important to make the distinction of what we're doing here. And in this case, it doesn't really matter as far as understanding intuitively what's going on with these waves, but I just wanted to make that distinction. So there's that with the partial derivatives. And the other thing I want to point out, I'll just use a different color now just to keep things fresh. So the other point I want to make is when we take the derivative with respect to x of a function, of this function, f of x, the ability for this wave to be composed of two different waves, this ability for it to be composed of two different waves, say like in the first few videos I made where waves were interfering with each other and either constructively or destructively interfering, adding together or canceling each other out. This is already built in to the fact that we're expressing this in terms of the derivatives. Derivatives. And how do we know that? Well, say f of x, say this is actually two functions added together. Oops. Undo. F of x equals two different functions. So let's, for fun, make them different colors, and we'll say, we'll just go through the alphabet. E, F, G, G of x plus, and then we'll continue with h of x, just moving through the alphabet, picking different letters. These letters don't mean anything, they're just ways to label these functions so we can say they're different. Say f of x equals, is the sum of these two other functions. And these two functions can represent, say this function represents the wave moving to the right, or the wave pulse moving to the right, and this function represents the wave pulse moving to the left. And if they're moving, I should add time as a these should also be functions of time, but for now I won't include that. But these are just two different waves that are interfering with each other. And so if we take the derivative of this, dx of f of x, we know that so I'll write this next step, I'll split this into its components. So we have g of x plus f of x, or h of x, excuse me, plus h of x, just these two different functions that add together to make our total f function. So I've substituted this in here, so these two are still equal to each other. I've just substituted the sum in for the f. So if you've taken a calculus course, and if you haven't, you've probably already stopped watching this video, but if not, if you've taken a calculus course, you know that this equals the derivative with respect to x of g of x plus the derivative with respect to x of h of x. And all I've said here is that you can do the derivative on different pieces of the wave, on different functions that add together to form your entire wave. So if we find a way to describe the way that a wave acts, requirements on the wave function, the function that describes the wave, it doesn't matter if we express it as the total wave or split it into several chunks that we know are adding together to form the wave. That it's self-consistent, and this property of interference is I would argue the most important property of a wave. And so I just wanted to point out that the first two videos fit into this math that we're building. And so just to summarize what I did in this video, I just clarified the difference between these two types of derivatives and said that if we're being mathematical and we're being careful with the way we describe things, that I've taken partial derivatives in the past two videos. And then the second part was just saying, putting into mathematical terms the fact that interference is still something that is consistent with these derivatives. And so hopefully maybe you're wondering about some of this, and hopefully this helped clarify some things about what's going on. And if this confuses you, this isn't essential to understanding well, I guess the partial derivative thing isn't essential to understanding sort of the big picture of what's going on, but the fact that this can still be interfering waves is going to be an important thing conceptually in future videos. So I've rambled enough for one video. In the next video, we'll continue trying to form a mathematical way of describing waves.